طيب تمام. أخباركم يا شباب؟ We have 5 minutes for your questions, whether they are related to the homework or for the anything in general that we had so far before we start. Anyone? Any questions? Let me check as we are getting closer to the quiz. How many of you received the textbook? Can you just raise a hand? Okay, 1/3, rough, more, okay, roughly 1/3. Okay. So let's see what happens during the remaining few days in here. But meanwhile, I'll make sure at least quiz number 1 can be solved completely by reading the slides that we have taken until you all get your textbooks. Okay. طيب, you can lower your hands unless you have questions, Hussein or Abdullah. Okay. So if there are no questions, then we are going to start today the basics of performance. We have done basics of aerodynamics, we have done basics of propulsion. So today we are going to see, inshallah, basics of the performance. That's going to be in chapter 4 and chapter 5. Chapter 4, which is a very short chapter with no examples, no problems whatsoever. It's just deriving the 3 equations of motion of the aircraft, just listing them, how they were obtained, and so that we can use them in chapter 5 to study the performance. So this is what we'll do in chapter 4. We're going to look at the equations of motions. We're going to look at the aircraft as a rigid body, and we're going to look at the forces on that rigid body, as well as the equations of motion that govern its motion. Okay. طيب. Now the forces that we have that affect the performance of the aircraft as a rigid body are, of course, the thrust, the drag, the lift, and the weight. But we need to agree, before we look at the equations, on their directions. What you see here is the direction when the aircraft is in straight and level flight. It's not climbing, it's not turning, nothing. But in general, the thrust doesn't have to be along the flight direction. Maybe it's not. And actually, this is the case in most aircraft. If you look at the engines, you will feel that the engines are not aligned with the center line of the aircraft. Sometimes they might be pointing downward a little bit or upward a little bit. There is an angle between the thrust and the flight direction. And when I say flight direction, I mean the direction of the speed, V infinity. Okay. Weight is always pointing downward, that's for sure. Whether the aircraft is climbing or not, it's toward the center of the earth. Drag is the force along the flight direction, and lift is normal to the flight direction. So let's move on from this straight and level. Let's take the condition when the aircraft is not straight and level. The aircraft is climbing, for example. In this case, the flight direction is along the tangent of the curve of the climb, maybe at an angle theta with the horizontal. The only force that's along this speed is the drag. By definition, drag is along the V infinity direction. The only force that's normal to this direction is the lift. By definition, it's normal to it. But the thrust doesn't have to be along the V direction. Maybe it's inclined with a very small angle epsilon. Okay, and the weight obviously is always downward. So that the angle between the weight and the normal is theta, if the angle between the velocity and the horizontal is theta. Because V infinity is perpendicular to the normal direction, So the weight is perpendicular to the horizontal direction, and the angle between them is theta and theta. So here's our agreement on the directions. Not only that, things can get a little bit more complicated. For example, for this condition, the thrust will have a component along the v direction of t cosine epsilon, and on the vertical would be t sine epsilon, which is okay. But what if the aircraft is not only climbing, but it's rolling to the right or to the left, or rolling, one wing is lower than the other wing? What does that mean? What if the aircraft is something like this? It's not only climbing, but also there is a roll angle phi, which is the decrease in the wing right angle compared to that of the left wing. So let's say the wing is also rotated by an angle phi. In this case, T is not always going to have two components, but it will also have three components, because there will be a component along the third direction. So I will resolve now the forces in terms of theta, phi, and epsilon. Okay, so if the plane of symmetry of the aircraft is rotated at an angle phi, if this is the left, then the component of the left in the vertical direction will be L cosine phi. In the horizontal direction will be L sine phi, and so on. Okay. Now, why I'm saying this? Because we are going to take an aircraft in a very general position, and we are going to write the three equations of motion. As a rigid body, the aircraft does have three equations of motion. What do you mean by equations of motion? It's Newton's second law, F equal ma. This vectorial equation has three components. It's up to us which directions we choose to write the three components. So typically, we would take the direction along the flight, which is the direction of the speed, the direction that's parallel to the curve of motion of the aircraft. So that would be our one direction. Then the normal to it, if the aircraft is rotating about a point, maybe it's pulling out of a dive like this, so that would be the second direction. And the third direction would be the one pointing right at you from this screen at this point, the third direction, okay, which might be there if the aircraft is rolling. So it's not going only up and down, but also turning to the right or turning to the left. This clear. So we have three directions, and we'll write Newton's second law in the three directions. Okay, I will write one, and then I will ask one of you to write the second one. I'm going to write Newton's second law in the parallel direction. This is the parallel, the v direction. Newton's second law is the force, obviously, is equal to the mass times the acceleration. So I will find all the forces in the parallel direction and the acceleration in the parallel direction. In the parallel direction, let's see, the only easy force to find is the drag, actually, because the drag is pointing opposite to v. So I have the drag, and I'm putting it with a minus sign because it's the opposite. If I take the forward to be positive, then the drag is negative. So it's minus d in here. This is the first force that I have. I also have the component of the thrust forward. Remember, the thrust doesn't have to be along the v, just like we had in here. The thrust has a component along the v of t cosine epsilon. So I will take that component as well, t cosine epsilon. So forward t cosine epsilon and backward d, t cosine epsilon minus d. Then the weight, which is downward, has an angle between it and the direction that I'm writing the equation in, the parallel direction. This angle here is the complement of theta. So the component of w here, if this is w cosine theta to the right, then w sine theta to the left. So it will be w sine theta backward. So I have t cosine epsilon minus d minus w sine theta. All of these are the forces. The lift doesn't contribute because it's normal to the flight direction by definition. So if this is the force, I'm putting it here, and I will need mass times the acceleration. Here is the mass. The acceleration along the tangential direction is the tangential acceleration. And it's simply the rate of change of the speed. It's dv by dt. And that's it. That's Newton's second law. That's the first equation. M multiplied by dv by dt is equal to t cosine epsilon, the only force forward, minus d backward, minus w sine theta backward. Any questions in the first equation?
Yes.
Yes.
Why we take t cosine and take only d, not d minus d cosine, d sine?
Why the what, please?
Why we take thrust cosine and drag without the angle?
Okay, because you see, this is the general case. You see that thrust is not along the drag. This is a very common misconception. By definition, we have defined the drag to be along the direction of the speed. Do you agree?
Okay, yeah.
So there is no angle. Drag is along the direction. Lift is normal to it. So lift doesn't contribute at all. But thrust, there is nothing that says that thrust has to be along the flight direction. It could be at an angle. In fact, it could be any angle. For example, you know the drones, the quadrotors, where you have 4 rotors rotating. What's the direction of the thrust? Upwards. What's the direction of the drone motion? It could be horizontal. So thrust doesn't have to be along the same direction of motion. So that's why we have t cosine epsilon, but d, we have whole d in there. Does this answer your question?
Yeah, but the angle of the thrust should be not from not until x-axis, right?
You're right, it's not from the x-axis. Remember, we are writing the equation along the tangent direction, right?
Yeah.
So it is the angle between the thrust and the tangent direction. Epsilon here is the angle between the thrust and the tangential direction. So this t in here, epsilon is actually this small angle, not that one. That one is called theta. Okay, so epsilon is this very small angle. Okay. Other questions?
Yes.
Yes.
It's related to the free body diagram, not the equation. Okay. Why for the lift we put cosine an angle? I mean, isn't the lift on its
Can I show it in here? This is a little bit more clear, would answer the question clearly.
Yeah.
Oh, you mean why for the left we put, oh, you mean here?
Yes, why for the left we put cosine with an angle? Because it's along
okay.
axis. I mean.
First, what is this angle? Phi here is the rolling angle. It's the angle below which the right wing will rotate from the horizontal. Okay, so the aircraft is rolling a little bit. Okay, now lift is normal to the wings in here, so that's the lift. So when we write the components along the vertical direction, it will be L cosine that angle. Do you agree if this is phi, or I need to prove it?
But if it was, I mean, with no rolling, it will be only lift.
Right. If the aircraft is not rolling, if it's just climbing like this, so left will be L. There will, just like you see in here, you see L. You don't see any phi or L cosine or something. The aircraft is climbing without rolling.
Yeah. Okay.
Does this answer?
Yeah.
Okay. So here, because the aircraft is climbing and rolling, I told you this is in like the general attitude. It does all the motion. So I have all the angles working here. I will derive it in general. And then when we specify a certain condition, we can put an angle to be 0 later on. Okay. Now let's write it in the normal direction. I need one volunteer, if that was clear, to write me the same equation. That means give me the force, give me the acceleration, but in the normal direction. Not in the tangential, in the normal direction. What do you have? Let's see. Let me see some raised hands. Okay. Mus'ab?
Yes, can you hear me?
Yeah, I can hear. Go ahead. Let's start with the forces. Write me the forces in the normal direction.
Let cosine phi
L cosine phi, positive, correct?
minus weight cosine theta
Minus W cosine theta, correct?
plus thrust sine episode cosine phi.
Correct. Plus the thrust sine epsilon cosine phi. So you have three components, which I don't have on this screen right now, but you have correctly written the three components. Now this should equal the mass times the acceleration in the normal direction, right?
Yes.
Not in the tangent. So what would be the acceleration in the normal direction, pointing toward the center? What did you have in your dynamics courses?
Fly stream square over r.
Correct. So you have correctly derived all of the second perpendicular equation. Here they are. Let's read what Mus'ab just said. The force is L cosine phi plus T sine epsilon cosine phi, that's the vertical component, minus W cosine theta, is equal to the mass times the acceleration, and the acceleration is the speed square over r, which is the radius. Perfect. Okay, just like any rigid body. Now, for the third equation, we have written only two, which is typically what you have written in your dynamics courses, but we have a third one now, because the aircraft might be climbing, but also turning to the right and left, just like what we have seen in here. Might be tipping. So I want to write the equation in the lateral direction as well, in that direction. Remember, the aircraft might be rotating up in a vertical circle with a radius r1, but maybe it's rotating on a horizontal circle as well in the same time with the radius r2. So the radius here is not necessarily the radius here. Okay, so let's draw the aircraft looking at it from the top. In order to see the motion in the horizontal plane, we are going to draw the aircraft looking at it from the top. It's the same aircraft, it's the same thing, but here I'm looking at it from the side, but now I want to look at it from the top. From the top, what I will see the horizontal motion of the aircraft. I will see V going this way, component in the horizontal direction. So I will write Newton's second law in the other direction, in the direction pointing towards the wing, the one that we haven't seen here. Remember, the wings are not leveled. One of them might be higher than the other because the aircraft is rotated. So when I look from the top, I will not see the lift as a point, I will see the horizontal component of the lift. So I will see the L sine phi. Do you agree with this? Because this is important. When I look at it from the top, I will see the horizontal component of the lift, and it will be L sine phi. It will be pointing towards the center. So here it is. L sine phi is pointing toward the center. And I will also look at the other component of the thrust that's pointing toward the center. Remember, the thrust doesn't have to be along the flight direction. Drag is in the parallel. Now drag will have a component. Okay, and now I can write Newton's second law. Sum the forces equal mass acceleration. L sine phi plus T sine epsilon cosine phi, all these are pointing downward. And this would equal the mass times the acceleration. Since the aircraft is moving along a curve on the horizontal plane as well, it is the mass times the v square over r. But remember, v in this direction, v in the parallel direction will have a component, v cosine theta. So that's why v cosine theta squared over r. This r here is not the same as this r. This is r when you move in the vertical plane, and this r when you look at the plane in the horizontal plane. And they don't have to be the same. Actually, one of them might be 0, for example. If the aircraft is going in this maneuver, it's going down and up, then R1 has a value, R2 is infinity. There is no R2, it's not turning to the right or to the left. Okay? So, and if the aircraft is rotating in a horizontal plane, just like in a circle, then in this case, R2 has a value, but R1 is 0 because it's not going up or down. So equation 3, equation 2, equation 1 are three equations of motion that define the motion of the aircraft at any altitude. This is all I have in chapter 4. Chapter 4 ends at this. What we have in chapter 5 is that we are going to specify this at different positions. Yes.
I have just one small question.
Okay, just a second. Let me answer one question first. I mean, when asking epsilon depends on the design or the flight condition. No, all the angles depend on the flight condition. Thetas, phis, epsilons depend on the flight condition. Because yes, you might have a sitting angle between the engine and the wing, for example, and that's a design thing. But the epsilon is defined with the flight direction, so the pilot can change that. It depends on the flight condition. Okay, now to your question. Who was that? Abdullah? Or who's talking?
Yes, Doctor.
Aywa,
You see, it says T sine epsilon cosine theta. Shouldn't T on the normal, like on the same line as L cosine theta be just T sine theta? That's enough. Why is it sine epsilon?
Let me follow you on here. You're saying, should T be only T cosine phi only? Is that what you're saying?
No, T sine. It should be T sine if it's on the y direction.
Let me look at the which one you are talking. You are not talking about this one.
No, the other one, the one after number 2. Yes, this one.
Okay.
Yeah.
Yes. Now, what you have here, which component you are talking about, the forward one or the lateral one?
It's the T sine epsilon cosine theta or cosine phi. Sorry.
Phi, cosine phi. You are talking about this. Okay. What about it?
Should it just be T sine phi? It's enough because it's in the y direction.
Let's see. Let's have a look at the aircraft room here. You see, if the thrust was pointing right at you, if it was pointing right at you, it is with the flight direction. Then it would be what you're saying, but in general, it's not. We said T could have a component horizontal. Here is the T because it's not along the flight direction. It's slightly at an angle epsilon. So it will have a horizontal component of T cosine phi and a vertical component of T sine phi. So phi actually is in the resolution of T. Do you agree that this could be our thrust vector or not? Because if the thrust is along the flight direction, you will see the thrust vector as a point.
No, it's not in our direction. It's up.
It has a component that's up. You see this T? It has two components. One forward and one upward, right?
Yes.
The one upward is the one that we are talking about. This one upward is rotated a little bit. This is actually the one that's upward. It's rotated a little bit. So it will have two components, one to the right and one upward. Now do you see?
Yes, I get it. Yes.
Okay.
Yes.
So what you see is simply because this component, the vertical component of T, has rotated a little bit with an angle phi.
Okay.
Yeah, very, very valid question. It might get confusing with three angles together.
Doctor.
Okay. Yes.
Sorry for interrupting, but
no.
Is there a way to put two slides together to show us two slides at once so we can?
Sure. Do you want this one and that one?
Yes. For example, like this, so we can understand it a bit.
Okay. Let me see. But it's going to be smaller. That's the only thing. Slides are going to be and they're already small enough. That's why. Let me see. Which two you want them beside each other? I can put them on the.
I mean, this one and the one that is facing from the top.
Okay, let me put them for you, and then we see that. but it's gonna be smaller. Let's take this one. In here I can. So I can make it smaller so that you can see two of them, but it's not gonna help. Let me see. You mean this one and that one together. No, I'll tell you what, I'll take this one and I'm gonna put it here right away. Just for clarification, so that you can answer your questions, and then we see what you want to have. Okay. This one. Okay. So your question?
I just want to put it like this so we can absorb the rolling. We can maybe understand.
Okay. Include the rolling as well. Okay. Okay. I'll make sure to do that in the one that I put on Blackboard, although you can put them beside each other. But at least you can bring them on a bigger scale, because once you start putting them together, it's going to be too small.
Yeah.
Okay. So this rolling that we are talking about here, this phi here is what will give you all the components. If there was no phi, you will not see this force and you will not see this force. They came from the rotation of the lift here and the rotation of the vertical thrust. Okay.
Doctor.
Yes.
The angle of epsilon is should be there while the plane is climbing. Always should be there.
The angle of epsilon is there no matter what. Even if the aircraft is flying straight and level, there might be an angle of epsilon.
So the angle of epsilon should not be 0, or should not be 1.
No, in general, what I'm saying in general. So the angle of climb is the theta that we have in here. But the angle of epsilon is the angle between theta and the flight, between the thrust and the flight direction. What I'm saying is it's not necessarily 0. It can be 1 degrees, it can be minus 1 degrees, by the way. It can be 0 degrees, it can be 2 degrees. So it's depending on the design that we have at the end. Okay, so it's not necessarily, and it can be actually more. The pilot can increase the angle of attack and it will be more. It can be 3, 4, 5, and 6 if you change the angle of attack.
Even the plane is move straight forward.
Yes, because when the aircraft is flying straight and level, let's go back to the straight and level. You mean this one? Actually, yes. There could be a misleading drawing that we always keep in mind. For straight and level, that means the aircraft is flying straight, but that doesn't mean necessarily that the thrust is forward. Okay, so there could be a small angle between the thrust and the drag, depending on the epsilon that we have. Okay, sometimes there are. Okay, but in general, as an assumption, we typically put that epsilon a very small value. We assume no thrust is in the same direction of that V, but what I'm telling you in some cases, it's not necessarily the case.
So the angle, if it is very small, we don't consider it.
Yes, for introductory course, for conceptual design, typically we don't include it. We say, okay, thrust goes with the equation with the forward speed. Okay. So what we will do now is we're going to basically do what exactly you have just mentioned. Now we're going to specify this to the straight and level flight. I will take the 3 equations. This is the end of chapter 4. That's it for chapter 4. It's not like a standalone chapter, but it's less simply the 3 equations. Then the whole of chapter 5 and chapter 6 is that we take these 3 equations and put them in whatever attitude we need. So let's do them in chapter 5 first for the straight and level flight, the one that you mentioned. And we will discuss some important value which is the required thrust as well. Okay, so let's go to the three equations. Here they are. I want you to specify them to straight and level flights. What do you mean by straight and level flights? What is theta in this case? If the aircraft is flying straight, theta would be
0.
Zero.
Zero.
Okay. And we agreed that epsilon will probably be very small, so let's put it 0 as well. Okay. What about phi? What about phi? Straight and level. Also phi is 0. Right? Straight and level. So basically all the angles are 0. Now what about the R's? If the aircraft is flying straight and level, what can you tell me about R1? If the aircraft is flying straight, what is the value of R1?
Infinity.
Infinity. Affinity. A straight line is a part of a circle with radius infinity. So R1 is of radius infinity. The same actually goes for R2, right? R2 will also be infinity. So if the R is infinity, then this value is 0. The acceleration is 0, so A2 will cancel. If the angles are zeros, then the signs are zeros, so this term will cancel. So the forces will cancel, A2 will cancel, so equation number 3 will totally cancel. We don't have equation number 3. It's 0 equals 0. What about equation number 2? Equation number 2, if you put the radius to be infinity, then the A normal will cancel. It's 0 because this is infinity. What about the angles? Cosine 0 is 1, but the sine is 0, cosine is 1. So this term cancels and you will end up with L times 1 minus W times 1 is equal to 0. That means lift is equal to 8. And if I go to the equation number 1, straight and level flight, no acceleration, this term is 0. So it's T times 1 minus G is equal to 0 because the sign is 0. So thrust is equal to drag. So for straight and level flights, we will simply get, when we put the radii infinity, all the angles are 0, I get lift is equal to 8, thrust is equal to drag. This is basically what you already have known without coming to class this morning. That didn't add much to your knowledge. But now you see it from the equation, because these two will change depending on the attitude of the aircraft. We'll get it when it's taking off, landing, turning right, turning left, and this will be slightly different. Okay. So for these conditions, an important design parameter would be what is the engine required? What's the size of the engine required to fly this aircraft straight and level? To answer this question, you will ask yourself, what's the amount of thrust required to fly this aircraft in straight and level? That means find me T that will satisfy these equations. Okay, so that's the question that we want to answer now. What is the value of thrust that's required to fly this aircraft straight and level? Now, the way to do this is to use these two equations. We don't have any other equations other than these two. Okay, so there are two ways. One is called the graphical way, and we're going to do this today. The other is an analytical way, and we're going to do it next. In the graphical way, we're going to say, okay, you want to fly this aircraft, good. At what speed? Let's say 400 feet per second. Okay, so at 400 feet per second, I will calculate the lift that makes it equal to the weight. Then from the lift, I will calculate the drag because they are related. CD and CL are related. And from that drag, the equation tells me the thrust is equal to that drag. So I will get you the thrust. This will tell you what's the thrust required and how big the engine should be to get that thrust. Okay, so that's the procedure that we will do in order to find the required thrust. choose any value of V infinity. From it, calculate CL. How do I calculate CL? Because lift is equal to the weight, so the CL would be obtained from this equation. The weight over rho V square S. Supposedly, I know the density outside. Supposedly, I know the wing area. I have assumed the speed, so I will get CL. Now I have CL, I will calculate the drag from CL. And from your reading in chapter 2 or from EE 220, we know that the drag depends on CL versus what's called the drag polar. The curve that relates the drag to the lift is called the drag polar. So when I have CL, I will get the CD. And once I have CD, I can calculate the drag, 1/2 rho V square SCD, and then that will equal the required thrust. If I do this for a certain speed, I can do it for any speed. Actually, I can do it for a whole range of speeds that can be used to give me a curve showing me the required thrust versus the speed. So I try several speed values, I do the same procedure, and I will get a curve showing me the thrust versus speed. Now, before we look at an example here, first I'd like to see if you have any questions. If not, I have a couple of questions.
What is the coefficient drag dot zero?
What is this CD naught? This one?
Yeah.
Okay. Now, this term is called the zero lift drag coefficient, CD naught, or the parasite drag coefficient. It is the drag the air wing that's going to have, even if the aircraft is not generating any lift. If CL is 0, it is the value of the drag. Okay. Now, if you recall, the drag curves were actually parabolic. The drag would decrease with the CL and then will increase from your study of chapter 2 or from A to 20. The drag curve starts with a value, decreases and increases again. So that's the representation of this equation. Think of this one as what is the drag at 0 angle of attack, 0 lift. Okay. This is the part of the drag that's due to lift. This is the part of the drag that comes because of the vortices at the tip. Once the wing starts to generate lift, it will add more drag. It's called the induced drag. So that's the second term. Where do I get CD naught and where do I get K? They are known from the airfoil. Every airfoil has an equation like this. Just like you have CL versus alpha, you have CD versus alpha, you have CD versus CL, and it's called the drag polar. Okay. Okay, actually, that was one of the questions that I was going to ask. What's CD naught and what's K in here? The other question was, what is S? What do you mean by S here?
Area of the landscape.
The area.
The planform area of the wing. When I look at the wing from the top, it's not the upper surface or the lower surface or the sum, it's the planform area of the wing. Okay, so let's have an example here. It says consider an aircraft with a certain weight, flying at a certain altitude, and here is the drag polar is given by this equation. So we know CD naught and we know the K. They are given for this aircraft. Find and draw the thrust required to fly the aircraft with a range of speeds from 400 to 1,000. Okay. So between 400 and 1,000, what would be the drag polar? What would be the thrust required? Let's state it another way. If I am the pilot and I want to fly the aircraft at 400 feet per second, what's the amount of thrust? Straight and level, so that the aircraft will not go up or will not go down when I fly at 30,000 feet. If I answer this, then what's the same value at 500 or 600 or 700 and so on? Okay. So let's see. We will apply the procedure. We will use one value, any value. I can start with the 400 or the 500. Here is just an example of one value. Altitude, 30,000 feet, here it's specified. Density at the altitude, where do you get the density?
From the appendix.
Appendix of standard atmosphere that you have in your textbook. Okay, so don't ask me in a quiz where is the density, it's not there. I'm not going to answer that question then. Get familiar with the textbook. And if you need any conversion units, make sure you put this on the sides. But here you will not, because it gives you in the British units. So we have V, we will calculate CL, since we know rho, S, and V, then we are going to have CL. I'm going to put CL in the drag polar, which is 0.015, 0.08 CL squared, so I will get the CG. So we have CG. And from CG, I'm going to calculate the drag, and I'm saying the drag is equal to thrust to be this value for this speed. You change V, you change T. You can put it in an Excel sheet, for example, these three equations, and you put V and you will get T. So you will get a set of points. Each point is a velocity and thrust, velocity and thrust, velocity and thrust. You can plot and you will have the curve. Any questions? Well, I have a question, very obvious question. Why does the thrust decrease and then increase again? Does that make sense? You see, this is the thrust and this is the velocity. This decrease here means in order to fly straight and level at a higher speed, because here it's like 350 and here it's 500. If you want to go faster, the thrusts need to be decreased, not increased. From this point to that point. In here, it makes sense. If you want to go faster, just increase the thrust. It will go up. Yeah, that makes sense. But what about this point? This area here? How can you explain this?
Because the curve of the polar drag.
Correct. Thank you. Because the thrust has nothing to do with the speed itself only. The thrust is there for straight and level to balance the drag. So depending, you see, thrust is there to balance the drag. So if the drag decreases with the speed, then thrust will decrease with the speed. And why would drag decrease with speed? Because to move from here to here, the pilot increases speed. To remain straight and level, he has to decrease the angle of attack. Okay, so that will decrease the drag pull, that will decrease the drag. And of course, this will decrease the thrust as well. You can see it here in the equation. The drag curve is parabolic. Okay, so that means it will go down and it will go up again with the CL. Okay, so here it will go down and then it will go up again. We call this point the minimum thrust point. It's an important point in a sense that if you want to fly the aircraft with the minimum thrust possible, you should fly at this speed, let's say 500 or whatever the value is. Okay. Now, that's not necessarily the case. It's not always required to fly at the minimum thrust, because what airlines care about is a different point. They don't care about the thrust, they care about the money they have to pay for the fuel. And that means they want the minimum power point. The minimum point at which, or the point at which you generate the minimum energy from the engine. Okay. So next time, inshallah, we're going to draw a similar curve, not the required thrust, but it's the required power. And you will see that the minimum power point is not the same as the minimum thrust point. Okay. And depending on what's the design objective of your design, we will choose one of them to be the design point of the aircraft. So in summary, we found that for straight and level flight, thrust decreases with the speed first until we get to the minimum thrust point, then it will increase again. And you can draw this curve for any aircraft. Actually, we have done the calcs here for a different example from what you have in the textbook, so that you can have two and compare. In the textbook, he chose like an altitude of 20,000 feet. Here is 30,000. You can simply change the density and see how would the curve change for this case. Okay. Any questions? Okay, Abdullah.
Doctor, is it in the question he assumed that will be 30 feet, the altitude?
No, yeah, what I'm saying is in a problem, I would definitely tell you what's the altitude. Okay? So we don't assume or something. In the textbook, he's just saying to you, so he says, let's assume an altitude. But in design, we must have an altitude specified, because I'm designing an aircraft flying at a certain altitude. So the altitude will be there. That's for sure.
Thanks, Doctor.
Okay. Marwan.
Yes, Doctor, just wanted to ask, does all the forces, we draw them coming out from the center of gravity always, right?
Yes, because we assume the aircraft is like a rigid body whose mass is exactly in a single point. I know that's not necessarily the case. This would affect only the stability and balance of the aircraft, but that we can look at after we have dimensions for the aircraft. Remember, at this point, we haven't designed the aircraft. We don't know how long it's going to be, how thick it's going to be, what's the diameter. So I see your point. They are not all coming from the CG, of course. The thrust is not coming out of the CG. It's coming from the center line of the engine. The drag is coming from the wing, whereas the weight is the only one pointing down from the CG. I see your point. But for the time being, since we haven't designed the aircraft yet, we'll assume they are out of the same point. But later on, we will take care of these distances between them.
Yeah, okay.
Okay, Musab?
Why the answer we get doesn't match with the curve here?
Because it's different. I told you it's a different example. You see on the curve, I intentionally picked a different altitude so you can try it for yourself. Here it's for 20,000 feet. Okay, here we have it is for 30,000 feet. So they don't match. Okay, does this answer your question?
Yes, yeah.
By the way, since you brought it, let me ask you a different question. You see this thrust here required to fly at 30,000 feet, it was 5,600 pounds. Whereas here in the example, in the textbook, 20,000 feet, obviously it was more than the 5,000. You see here it was like, I don't know, 8,000 or something. Okay, this is 10,000. So why do you think it was more? Or does it make sense it's more? At 20,000 feet, the thrust required is more than that at 30,000 feet. The thrust required to fly straight and level. Why is that?
Because of the air density.
Because of air density increases the drag. It's as simple as this. Air density increasing drag. So if you want to save fuel, the aircraft should go higher to reduce thrusts during the longest phase of the flight, which is the cruise phase. Okay. Okay, great. Okay, Shabab. So any other questions? Don't have any raised hands. So inshallah, you have until midnight today to submit the homework. Don't forget that. Don't forget your quiz next week inshallah, right after the holiday. So كل عام وانتم بخير ويا رب يديم علينا نعمة ويحفظ المملكة. And get a well-deserved break, because apparently that's the only break that you are gonna get until the end of the semester. Okay, so I will see you inshallah on Monday.
Thank you.
شكرا يا شباب. مع السلامة.